Now we turn to abstract data types. This is where we separate what a structure promises to do from how it is built inside. An abstract data type, or a DT, is a contract. It lists the operation names and what each one promises to do. The storage is hidden. Think of a car. The pedals are the interface. The engine is the implementation. The client code on the left only knows three operations: add, contains, and size. Those live in the amber box, the contract. Right now an array is plugged in behind the contract. Three other backends wait, grayed out. None of them is connected yet. Now we swap the plug. We pull out the array and plug in a hash table instead. Look at the client cable and the three ports. They did not move. The client still calls add, contains, and size in the same way. This wall between the contract and the storage is the whole point. It lets us change the machinery later without touching a single line of client code. Let us make this real with the set. A set is a bag of distinct values. It has no order and it is bounded by a cap. Look at the picture. 3, 1, 4, 5, 9, 2, 6. If you try to add a second one, it is simply dropped. The set gives us three operations. The first is add of x. It inserts x only if x is not already there. It returns 1 if x is a member after the call, and 0 if the set was full and had to reject the new value. The second operation is contains of x. It asks a simple question: is x a member of the set? It returns true or false. The third operation is size. It tells us how many distinct elements the set holds. That number equals the count of successful adds. And this is the rule that never breaks, the invariant. Every element appears at most once, and the size stays between 0 and the cap. Every correct build of the set, whether array, tree, or hash, must keep both of these true. Same set contract, different machinery inside, different costs, but the same client calls. This table shows 4 ways to build the very same set and the price each one pays for its work. The first backend is an unsorted array or list. To check contains, it must scan every value, so the cost is big. O of n adding is also big. O of n, it keeps no order. The second is a sorted array. Because it is sorted, contains can jump around and cut the work in half each step, so it costs big O of log n, but adding is slow, big O of n, because we must shift values to keep the order. The third is a balanced binary search tree. Here both contains and add cost big O of log, and so it stays fast for both operations, and it keeps the values sorted. The fourth is a hash table. On average, contains and add each cost big O of 1, which is the fastest class of all. The trade-off is that it keeps no order. So choosing a data structure really means choosing one implementation of an ADT. You pick the one that makes your most common operations land in a cheap growth class. We build that decision framework in Chapter 21. Before we read any C, let us learn the notation that every chapter uses. It is CLRS style and it starts counting at index 0. A single equals sign means assignment. A double equals sign means a test for equality. A dot before a name means a field. A double slash starts a comment, and nil means the null reference. Now read the algorithm itself. Set contains walks the items from index 0 up to size -1. At each step it checks, is this item equal to x? If yes, it returns true right away. If the loop finishes with no match, it returns false because it has scanned everything. We show this as pseudocode because it is a genuine algorithm, a linear scan. Later, simple pointer work will skip straight to see we add pseudocode only when it makes an algorithm clearer, never just to fill a slide. Now the same set in real C, this whole struct plus 3 functions, is one implementation behind the wall. The set stores its values in an array called items. The array has room for cap values. The struct also keeps a counter called size. It records how many values are stored right now, so a set is just an array plus a count. The first function is setContains. It takes the set and a value x, and it answers whether x is already a member. Inside, a loop checks each value in turn. If items at index I is equal to x, the function returns true straight away. If the loop finishes and finds no match, the function returns false. That is the linear scan we saw in the pseudocode. The second function is setAdd. First it calls setContains. If x is already a member, it returns 1 and does nothing else. No duplicates. Next it checks whether the set is full. If size is equal to cap, there is no room, so it returns 0 and rejects the new value. Otherwise there is room. It stores x in the next free slot and it bumps size up by 1. The plus after size is a post increment. It uses the current slot first, then adds 1 to size. The third function is setSize. It simply returns the counter. 3 short functions and the whole set contract is kept. Let us trace the code by hand. We feed a fresh, empty set these 4 values in order, 3, 1, 4, and 1 again. Before we read the table, try to predict. What does the set hold at the end and what is its size? Watch that last one. Step 1, we call add of 3. First contains checks, is 3 there? No, it is false. So we insert 3. The set now holds 3 and the size is 1. Step 2, we call add of 1. Contains checks for 1 and finds nothing, so it is false. We insert 1. The set now holds 3 and 1 and the size is 2. Step 3, we call add of 4. Again contains is false, so we insert 4. The set now holds 3, 1, and 4 and the size is 3. Step 4 is the interesting one. We call add of 1 again. This time contains checks for 1 and it is true because 1 is already a member. So add does nothing. It is a no-op. The set stays 3, 1, 4 and the size stays at 3. That last step is the invariant doing its job. Because 1 was already a member, add inserted nothing and the size did not move. Every correct set, whether array, tree, or hash, must keep this promise. Each element appears at most once. This is the same add trace, but now you finish it. The first 2 rows are done for you. Row 1 adds 7. The set was empty, so 7 goes in and the size becomes 1. Row 2 adds 3. 3 is not in the set yet, so 3 goes in too. Now the set holds 7 and 3 and the size is 2. Now row 3 is your turn. It adds 7 again. Before you look, ask one question. Is 7 already in the set? Think about what add should do here. Row 4 is also yours. It adds 8. Ask the same 2 questions. Is 8 already in the set? And is there still room to store it? Let us check your answers. In row 3 contains 7 is true. 7 is already there. So add does nothing and the size stays 2. In row 4 contains 8 is false and there is room. So we store 8. The set becomes 7, 3, and 8 and the size is 3. We just stored the elements in an array of integers. So the array starts to feel like the set itself. This is a common mix-up, and we should clear it up now. An array is only one of 4 ways to build a set. You could also use a linked list, a hash table, or a tree. The array is a way to build a set. It is not the set. So what is the set? It is the 3 operations, add, contains, and size, plus the 2 rules. No duplicates and the size stays inside the capacity. Keep the pedals and the engine apart. Those 3 operations are the set. The array is just today's engine. Let us run the set for real. We feed it 10 numbers and 3 of them repeat. So the set should keep only the 7 different ones. These print lines ask the set some questions and show the answers. The first line says size equals 7. 10 numbers went in, but 3 were duplicates, so they were dropped. Only the 7 distinct values remain. Next contains 4 prints 1. 1 means true, so the value 4 is a member of the set. Then contains 7 prints 0. 0 means false, so 7 is not in the set, we never added it. Now we add 8. It prints 1, which means 8 was inserted. The set is now full. It holds 8 values and the capacity is 8. Next we try to add 7. It prints 0. The set is full, so the new value 7 is rejected. It is not thrown away in silence. The 0 tells you it was refused. The last line says size equals 8. A rejected add does not change the size, and every run prints these same lines. There are no random addresses. That is our rule for almost every program in this course. Let's do a quick check. We have 4 statements about the set. Some belong to the set as an idea of the contract. Others are just details of this array version. Statement A, adding a duplicate, does nothing. Statement B, elements live in the items array from index 0 up to size. Statement C contains returns a true or false value. Statement D contains scans from left to right. Take a moment and sort them. Which 2 describe the contract, the promise that never changes, and which 2 describe only how this array happens to work. Decide before you see the answer. Let us check together. Statement A and Statement C are the contract. Any set must reject duplicates and must answer contains. Statement B and Statement D are just this array. A hash table would keep the same promise, but store the values in a different place and search in a different way.